बाहेर निघालं मग तिथून नाही समजा
Good evening, all. I hope you all doing great. We'll start. So, Shashank sir, you can take over the class.
So good evening, everyone. Welcome to day 12. So today we'll continue on that time series project. Let us discuss, the models, AR, MA, and all those things. Right. So let me share the screen. Just give me a minute. Share. Okay. Right. So we were discussing the concept on time series, right? And we have just, on a brief outlet, I have given the just an introduction where what is exactly time series, right? After we had a discussion on the XGBoost. So these are few models which we actually have that these kinds of models do exist. So first AR, MA, then ARMA and ARIMA and then SARIMA. So I told what are those, and we have just seen what is an introduction to the time series and all those things, right? How things work out in the time series. And coming to the libraries part, so these are a few important libraries which the time series actually works on. And we have also seen the data set, right? Which basically consists of the number of trucks sold to the years. Okay, so this is what the data set was actually about. So now, so going forward, we have changed one important thing. What we have applied is we have changed months to months and years, or we can say we have splitted both months and years. Okay, instead of having, for example, you can see 3rd May, right? So instead of that, we have kept a date, right? But what we have done is we have made into two different columns where there is month as well as year. So which is here, for example, you can see Jan, right, 2003, Feb 2003, right? So like that, we have splitted the data into columns. So that is one thing what we have actually done. Now, after that, we have plotted a graph, and I have already told you that when we see the graph, the most important thing is the consistent growth, right? So that is very important with not much of ups and downs in the data. So that is a very important aspect when we talk about the time series data, which can be used for predictions. So this is a very important aspect which has to be kept in mind. So for that, I've also given some brief intro that what exactly happens in a time series data, right? The most important thing is the concept of stationary and autocorrelation, right? And for checking of this stationary, we are using this the concept of, or I can say the test called Dickey-Fuller test. So I think till here I've just told, and let us also have some small idea about what is this autocorrelation and what is this concept of stationary. That is what I have actually told you, right? So then we'll continue the session I told, right? So that is what we are going to do now. Okay. Just give me a minute. Let me. Okay, fine. So now let us understand that what is this concept of stationary. So I'll try to keep it very brief. Okay. So to make you to understand an outer picture, what is happening in this time series, and how things work out. Okay. So now if I have to talk about what is exactly stationary. Okay. Right. What is exactly stationary? Why we are using the word or the keyword called stationary? That is very important to understand. Right. So I think everybody knows some statistical concept, for example, like mean and variance. Right. So mean and variance. This is the most common. Maybe maybe correlation you would have heard, but autocorrelation, a very few would have heard. Okay, fine. So let me come to mean and variance. Fine. So there are a concept called as mean and variance. So that we already know. Mean exists in measures of central tendency. Variance exists in the measures of dispersion. Now, if we have to tell that the particular data is stationary, the data has to be, right, when you plot on the graph, you can see that the mean, variance, and the autocorrelation has to be constant. Here I have not mentioned mean. Actually, mean also, exist. So it is mean, variance, and autocorrelation. So these three things should be constant over a period of time. Okay. So that is in where we call the data as stationary. Now, what we have to understand is why this concept is used in such a way that we are saying that it should be constant over a period of time. Because if they are constant over a period of time, what happens is concepts like trends, right? Seasonality, right? And any constraints which are existing in the data can be eliminated. That means, or they are not existing. For example, trends and seasonality. To avoid this, right, we say that the data has to be stationary. For that, our mean, variance, and autocorrelation has to be constant. So this is the main picture of why we say it is a stationary. Now, going to the so maybe variance you have already understood mean, so I'm not touching mean and variance part. So let us understand what is autocorrelation. Okay, so in a simple terms, or in a simple way, if we say that in a time series data, right, uh, you know how, in a very simple term I want to tell. So autocorrelation, because we call as autocorrelation serial correlation. So I can say in a very simple definition. I think I've not mentioned here. I guess I've just mentioned the lags. Okay, so a very simple definition of autocorrelation is I can say the relationship between a time series and its lagged values. Okay, so the relationship between the time series data and its lagged values, right, depend on the lag, not on the time. Okay, when the correlation is computed. This is what the actual definition of autocorrelation. So for example, when we say that, this time series data, I'll tell you what is that lag actually also. So the time series data, and when we calculate the correlation between time series data and the lagged values, right? The correlation depends upon the lag, but not the time. Okay, that is what basically autocorrelation is. So if this happens, we can say that the data is having autocorrelation. Okay, so now I'll explain it even more detail when I talk about lag and all those things. Okay, so now, so actually, when we talk about stationary, there are two important things. One is the strict stationary and the weak stationary. So strict is like in a particular the the distribution of the data has to be very strong, or it should follow a distribution, right? So that we are following it very strictly. So the names itself tells strict and weak. So little more lenience, right, is given in the weak stationary part. Now, there are two important tests which actually are used. Okay, so the first one is the Dickey-Fuller test, or DF test we say, or Dickey-Fuller. And apart from that, we have one more test which is actually used, which is KPSS. Okay, so that is very rarely used, but it exists. So next is the most important thing is to understand that if the data is not stationary. Okay, let us not dive into that much, but I'll just tell you some of the things which have to be done if the data is not stationary. The most important thing is the differencing, right? So that means removing the trends, and by applying the log transformations, then applying the seasonal decompositions. That means whatever the seasonal changes are happening on wherever the seasonal changes are happening, removing that particular part. That is what basically we say it as seasonal decomposition. And one more important thing is the detrending. That means removing any long-term trends, right? So this one we are going to do, right? So actually, how do we remove long-term trends is by using linear regression. Okay, so yeah, that is what we are going to do to achieve the stationary pattern. Now, let us understand that I'll come to this lag part little later. Keep that in the memory. Okay. So I think here I've mentioned also stationary means that autocorrelation lag depends on the lag value, but not the time. Yeah. So this much you remember. Okay. Here K is the lag value. Okay. T is the time. Okay. Yeah. So this much you remember for time being. Again, I'll explain. Okay. Because not everything I explain at once, it can be a little confusing. So yeah, next part what I'll speak is about the Dickey-Fuller test. So what does this test do? So by this time you would have understood that what does this test do. First of all, this test actually helps you to check whether the data is following the statistical method of stationary or not, right? So that is what basically the Dickey-Fuller test actually uses, right? So now what it usually does is it checks for the stochastic trend. Okay, right. So let us not talk that much also about that, right? So we actually build a hypothesis, as you can see here, that H0 we are taking as a time series is not stationary, and alternative is something where we take the time series as stationary. So we check the data and we plot the we apply the analysis and Dickey-Fuller test, and we are going to check whether our value is actually less than your p-value, right? So your alpha value, which is lesser than the p-value. So 0.05 is called as the alpha value, which is called as a rejection region, right? It is called as a rejection region, right? So this alpha value, our p-value is nothing but the probability value. So if our probability value is lesser, right? So then, right, we are rejecting, right? And that is what we are trying to apply. So now, the most important thing is to check whether by using this test. It's a very easy way to check. So if I just go down, sorry. So now if I just check for the, the values, right? So if I just apply, if you see in a very simple language, you can see that the AD Fuller is the function. Okay. So here, if we apply the AD Fuller test, okay, what happens is at 1%, 5%, and 10% it is giving, which is the alpha value, which is the rejection region. So here, when we apply the Dickey-Fuller test, you can see that the alpha values are, the p-values are, probability values are very big. So that is what my conclusion is also. The p-value is actually 0.99. Ayo, we have to get the p-value which is less than our, our alpha value. So it should be basically less than 0.05, but the alpha value, so the p value is more, right? It's so much more. So by that we can confirm, right, by a very small test, which is the ADF, which is the key filler test. So if you just apply this, we can see that our p value is more than our alpha value. Then we can conclude that that means we are basically accepting the null hypothesis. Okay. So if your p value is lesser than your 0.05, then we accept, or you can say we can reject the null hypothesis and accept the alternative hypothesis. Okay, which is the time series is stationary. But if your p value is greater than your alpha value, then we actually accept the null hypothesis, which is the data is not stationary. Okay, so that is what we are going to do. Now, here you can see that the data is not a stationary series. That means there either a trend is existing or there is a seasonality. Something is there. Something is there which we have to observe. Okay. Now, the next thing is bivariate analysis we are going to do. So performing the decomposition of data, because I just told you, seasonal decomposition and all, we are trying to do, or we will do that. Now, so by performing the seasonal decomposition or decomposition of data, if there exists a seasonality and split the data accordingly, observe that the number of trucks sold vary on monthly basis. A stacked plot actually can give you a clear reflection. So that we will see by plotting a graph. Okay. So the next thing what we are trying to do is, we are going to understand by monthly, right? By every month, how much of sales are happening for which kind of year. So we are splitting the data. Okay. So we are splitting the data, keep creating a pivot table. Okay. So for pivot table, you have to use the pandas library. Okay. In Excel, you would have heard about this word pivot table, right? So creating in a table format. Now, going to the next part, which is here, what has happened is the sales are showing in April, August, December, and all. So just we are reordering in the form of reindex. Okay. So I think you'll be understanding it very easily. So it's just we are creating a reindex. What this does is we can give in whatever index we want. Okay. Usually the month starts from January, right? So sorry, the year starts with January, right? So January to December, we can rearrange the data. Okay. Just reindexing or rearranging I'm doing. Okay. So nothing fancy or nothing out of the blue, right? So now this is done. Now the next thing what we have to do is we have to plot a graph. Here, plotting the graph is very important to check whether how the data is actually reflecting, right? So now you can see that the data is not constant for every year. It is like ups and downs, a lot of ups and downs are happening. So this indicates that there is some seasonality which is in the data set or which is existing in the data. So now we have to figure out this seasonality and we have to remove the trend and seasonality in order to apply the models. Right, so that is what the next agenda is basically about. Now we can see when we plot a box plot, right? So we just plot a box plot for each and every year, right? So for each and every year, it has taken. We are building a box plot. So this is what we are trying to do. So going to the next part, right? So after we have rearranged into a pivot table, what we are exactly doing here is we are trying to analyze the data. Okay. So here again, once after plotting the box plot, right, we have again built a table. Okay. So here to indicate the yearly sales. Okay. So here we have taken the monthly sales. Now we can see here we have calculated per month. Okay. Here the month is in the main focus and year at the top. But here we have given the main focus to the year. Okay, nothing much difference. Okay, indexing differs. Here you can see and is going up and down. Here indexing we are giving for month, right? And here we are giving the index for year. That's it only. So year will be in the main focus. That's it. Very small difference. Just to see or observe the data. Same pivot table we are using. Okay, so nothing much. Thing we are doing. Right. So now let us go down. Okay. Now per year, we are trying to plot the graph. So before for monthly, we have plot the graph, right? To observe the seasonality or the seasonal changes or to see how the data is actually, performing, right? Now we are taking per year, right? So now what happens if we put per year also, you can see there is a lot of ups and downs also in the data, which is existing. That is why the data is actually non-stationary. right? It is not in a stationary form. So the same thing, we are plotting a box plot. Okay. So if you see the box plot, there are lots of ups and downs again in the data set. Okay. So that is where we can see that there's the continuity or the consistency is not there. What is stationary? Stationary is nothing but consistency in the data. That's it only, right? But the statistical term is stationary, and we have methods to say that mean variance and autocorrelation are constant over a period of time, right? Then we are calling it as stationary. So it's a technical statistical term we are speaking. But in a very layman language, if we speak, the data has to be consistent, right? That's it only. That is what basically the stationary concept is basically about. Fine. So now let us go down with the inference, right? So what we have done. So basically the sales are increasing every year. So that we can already see with our eyes. And by the graphs, we can also observe that there are a few months which there are a lot of peaks. Okay, particularly July and August. So what is happening is mean and variance is shooting up for these particular 2 months compared to the other months. Now, with this 12-month seasonal cycle is present as mean of each month, each month year on year starts with an increasing trend in the beginning of the year and drops towards the end. So the trend is, increasing and decreasing, increasing and decreasing. So, there is no consistency, what is happening inside the sales part. Now, we bring in the decomposition part. Okay. Now, let us plot the seasonal decomposition. So the seasonal decomposition is in the function, this SM function, okay, stats models. So if we plot the seasonal decomposition, it will plot a graph, okay. So everything we can use it by understanding the graph, okay. So here you can see that, see the trend line. Trend is constantly going up. And if you see the seasonal changes, there is lots of ups and downs, right? And the sales are, going, it's increasing, but there is lots of, again, ups and downs which are happening in the sales also. So what we'll understand by this, graphs, what actually are given by the function, which is the seasonal decompose, which we have constructed or which we have built. So what is the inference we are going to get, and what can we, conclude by this graph, right? So very important thing what we can conclude is there is existence of linear trend, okay? And seasonality is also clearly visible, right? So what happens is, guys, very simple to understand. See, if there is a lot of trend in the data and a lot of seasonality in the data, what happens is it is very difficult to capture the pattern in the data, or you can say a particular way of things, how things are performing. So how the data is actually behaving, how the data is actually how the sales are actually happening, what is the pattern, or what is the behavior it is following, that will be difficult to capture, right, for the statistical models if we are having trend and seasonality in the data, right? So that is why the existence of trend and seasonality has to be removed if the data is having that features. That is only we are calling it as non-stationary. Okay, so if the data is stationary, definitely the trend and seasonality will not be existing in the data set. Okay, so that is what the whole picture is. Now, coming to how to make the time series stationary. So I already told you. So there is a certain concept called as differentiation, right? What exactly happens in this differentiation is we are going to apply a lag. Okay. So now I think this is the right time for me to tell you also that what is a lag. Okay. So anyway, Dickey-Fuller test and all those you have already understood, right? Now let us understand what is lag in a time series data. Okay. So I think because this is the right time exactly to speak about lag, because when we are applying that the data is non-stationary and we are applying the methods, so we have to understand that what happens in a lag first, then we can apply how lag can be applied in the differencing techniques. Now, what exactly is lag? In a very simple terms, this is basically saying that lag actually refers to the time difference, okay, or interval, right? We also speak about the interval. So if you can see here, we are speaking about the interval, which is, yt and yt minus 1. That is, we are taking the difference. That means yt minus 1 is the previous observation, right? So what we are actually trying to do is we are trying to take the time difference, right, of the times, which is, yt plus 1, yt plus 2, and so on, right? So if you go back, it will be yt minus 1, yt minus 2, right? So now what is exactly it is? Lag refers basically to the time difference or interval between an observation and the series, right? Now, in our simple terms, lags are basically used for modeling the relationships in a very simple terms, right? So what happens, or how I can understand? So it is basically, trying to understand the relationship between the past and present. Okay, this is a very simple layman terminology. So understanding the relationship between the past and the present. Okay, so what happens is this will actually help you to identify this trends and patterns in the data, or trend or seasonality in the data. Now, what happens is if we take one difference, we take that there is one lag difference. Okay, so let us little rephrase. Okay, so I'll tell you why lags are important. Okay, why lags are important. Now, when we talk about the past and present, okay, when we talk about the past and present, right? So what this lag does is, the concept of lag, what does it do is, it will capture any dependencies are there between the past to the present. Okay, so for example, we say, usually, right? So some people, it's quotes and all this. Your past depends, your past should not define your future. That is what exactly lag is. So whatever any relationship is there between your past to your present, okay, that differences, or that I should not say differences, that according to formula we are calculating differences, but to understand the relationship between your past and your present, right? That relationship, that dependency is captured, or that is what is basically lag is. Okay, so capturing the dependency between your past and the present. Now, one small example I can give is, you can see the stock prices, right? So basically, the stock prices have lags. Why? Because they have the dependency on the past data. Whatever is having dependency on the past data, it is having a relationship. It is basically called as a lag. Okay, so best example is stock prices. I cannot give a very good example than stock prices. Okay, so I have to think for some better examples. But if I have to instantly tell that what is a very best example, stock prices is a very good example to understand lag in a time series, because it depends upon the previous stock price. Your current stock price depends upon your previous stock price. It depends. So it is having a relationship with that. It's with its past. Then it is having a lag. Okay. Now, so I think this. I think I've tried to simplify it so much to make you to understand what is a lag. Okay. Fine. So if we don't capture the lag, or if we don't define this lag, right, it is very difficult to predict the future values. So if the lag is existing, okay, if it is not existing, no problem at all. If the values are independent of each other, if the values are independent of each other, right, there is no need to capture the lag. Okay, but if the values are dependent upon each other, then we have to capture the lag in order to stabilize the workflow, or stabilize the flow of the data. Okay, so this is what basically the picture of lag is. So yeah, now what exactly, let me go down, okay, to the data part. Now, here you can see that, yeah, let us start with the differencing part. So we are applying the method of differencing. Okay. Now, let us plot the graph without the differencing. So we are plotting the years and the sales. Okay. First, we are plotting it, right, for the entire data without applying the differencing. So that's what I mentioned, non-differenced full time series data. Correct. After that, I am plotting with the difference, with the difference here. You can see here. Let me show you the exact difference. So the sales underscore TS is the function. So I can say the variable name, right? For that, I am applying differencing function. See, DIFF is the function. See the syntax difference. That's why I'm just trying to show you like that. So everything is same what I have done. Only part is just without, I have plotted only the variable. But here, what I'm trying to do is I'm trying to plot the differencing now. I'm applying the differencing function. Very easy to implement actually, very easily you can understand. So we are applying this differencing function, right? And we are applying the period, which is 1. That means we are applying 1 lag. Okay, we are applying 1 lag to the data set. Now you can see the graph, it has changed. See the graph, right? Now, let us apply 1 more lag to it, which even more has changed. See carefully. Okay. Now, what can we understand by this? Is we observe that seasonality even after differencing, meaning the variance in the data seems to be increasing, right? This suggests for a log transformation. Why? Because there is one small thing I just wanted to tell you. See the data set, right? And after see this, there are even more ups and downs in the data. That means the lag is not working that much. The method of differencing is not working that much. Okay, for identifying the lags in the data set. Now, that is why next best thing is, see, there are 4 methods. Okay, we try to apply one by one and check what is the best possible thing what we can do. Okay, whatever are there we can apply. No, we cannot do anything else which is not existing, right? Either we have to find a new one, right? We have to do research and find a new method. If that is what actually happens in the industry also. Sometimes if you don't have, the research and development team takes over to develop a new model if something is not existing, which is not sufficient to analyze your data. Now, coming to the next part, since the differencing is not a very good suitable, see the changes actually. A lot of changes are happening again, up and down and all. Now, what is happening now is we are applying the log transformations. Okay, so log transformation will apply the logarithm 10 to the data set. Now, when we apply the data, when we apply the log transformations, right? So we can observe that the seasonality and trend even after applying the log transformation. Now we have just applied the log transformation. Now we are going to go one step ahead. Okay, so what is that one step? What is it one step ahead is? We are applying the log transformation. Along with that, we are applying the lag. Okay, so in the lag, actually, we have the method of log transformation to obtain to stationary. Right now, what is happening is we are applying the lag 1 now. We are applying the lag 1. So if we apply the lag 1, now the complete picture has changed in the data. So now this line is basically about applying the log transformation, right, with lag 1 or 1 lag. I can say lag 1 or 1 lag, which is more flexible. You can, with lag k is equal to 1, we say. Okay, we usually denote with k. Now you can see that there's a lot of difference in the data set. Now, let me apply lag 2. Okay, again, you can see there is a lot of difference in the data set. Right now, what is happening basically is there is now almost a consistency which is happening in the data set. So there is a similar kind of consistency which is happening throughout the data set now. So almost the trend and the seasonality are somewhat removed. So which is better. So now see this graph. There's a continuous, process or a continuity in the diagram, or I can say the figure. Now, if you see that before, where is my with applying the differencing techniques with the lag 2, see the difference. There's a lot of okay, so you have a lot of you can again see that there is no there is no consistency in the figure or the graph or the diagram. But here, when you apply the different, log differentiation with lag 2, it is much more better compared to lag 1, and there is consistency in the data set. This has to be done before applying any models. Okay. Now let me go to the next model. Sorry, let me go to the next model, which is the auto-regressive model. Okay. So just before that, if you have, I've been continuously teaching. I didn't ask you any doubts. So if you have any doubts, you can just ask me. Okay. So somebody texted me for attendance. That attendance will be shared, ma'am, at 8:30, something like that. You can just please wait for the attendance sheet. So apart from that, please ask me doubts. Apart from that attendance thing, please ask me any doubts if you have. We can say it as outlier, yes, but yeah, which is not supposed to be existing in the data set is actually outlier. Yes, correct. Yes, I agree with you. Yes. We don't usually say that. We, in statistical terminology, we say it as a trend and seasonality. See, what these will do is it will actually, block the smooth flow of the data. See, if the data is in a smooth flow, for prediction, it will become very easy. But sometimes this trends and seasonalities, what they happen is unnecessary fluctuations in the data. So with unnecessary fluctuations in the data, it is very difficult to predict the future values. For example, like predicting a sales, right? So it is very difficult to do that. So that is the reason we try to remove this trend and seasonality in the data by applying these statistical methods. And yeah, so that is why we have definitely, we should be behind that stationary and non-stationary, apply the Dickey Fuller test and all those things. So it's a process that we do, and I can say, yeah, I agree with you. It's actually called as an outlier also. I didn't get your question. A seasonality also takes the sentiment analysis. I didn't get that. It just rephrase the question. The seasonality also takes sentiment analysis for analyzing the data. Yeah, you can take. That's what your question is. Getting it properly. Also, take sentiment analysis. What does it mean? Are you asking like, can we do, for sentiment analysis, can we apply the seasonality for sentiment analysis? That is what the question for that. I don't get the question actually. The seasonality also takes it. Okay, fine. So for sentiment analysis, can we take seasonality into account? That is what. So basically, sentiment analysis is analyzing the text. So we are trying to analyze the text. So and basically this seasonality is basically used for time series data. So I wouldn't agree on that part actually. So any other um, so anybody has any other question, just can ask me. So once, if maybe a couple of minutes more, I'll wait. So once if you don't have anything, we can we'll go with the first model, AR model. So till now, what we have done is we just checked for the seasonality, whether the data is seasonal or not. Sorry, stationary. Sorry, my bad. So whether the data is stationary or not. If it is stationary, well and good. If it is stationary, well and good. So if it is not stationary, what should we do? So which kind of method we have to apply? So we have to bring the lag into picture and we have to apply the differencing techniques, log transformations. So we try to convert it to stationary and then we try to move forward with the models. So if the data is directly in a stationary form, we are lucky, we can just move forward directly with the model building. So this is what the whole scenario basically is. I think we can go ahead. No questions, I guess. Okay, fine. So let me continue. So the first model is basically about the auto-regressive model. Just a minute. Now, so this model explanation, I'll keep it very simple. Okay. So I'll just try to tell you that why this model is used. Okay. That is the first main agenda what I have. So I'll tell you why this model is used and why it is existing and what it does. Okay. So I'm not going to much of formulas, much of those stuff. I'm not going to go. I think I got a question maybe. Optimization and hyperparametric tuning, we already discussed. I think you are attending the sessions. I think you have not attended my previous sessions, I guess. We have already discussed on all these things. What's your name? Pavan Kalyan. So we already have discussed this. Something related to our concepts, what we are discussing. If you have anything, you can ask me. Okay, because it's it will deviate from what we are trying to do. Because I've went on a process. Okay, so one step after the other, which kinds of algorithms have to be implemented, and then so I've gone with that. So maybe we can discuss this last. Okay, I'll just keep this in memory. Okay, fine. So let me just talk about the auto-regressive model. Okay, so what is this auto-regressive model first of all, and why this actually exists? Let us try and understand that. Now, to keep it very simple, okay, what is auto-regressive? See, why we are using the word auto, there is a meaning for it, okay? So to understand in a simple terms, okay, so I can say that the current value, okay, I'll simplify it in a very simple way. So statistically, to understand, the current value is or can be expressed. Okay, so if the current value, right, that means, for example, if you're talking about sales, okay, some product sales. So for example, I'm selling the, I want to sell a product today. Okay, that means the current scenario. So my current value or my current product sales can be represented, right, as a linear combination of its past, right? So that means by a linear combination of the lagged variables. Okay. So here, I think in formula you can see also, I just don't want to touch, but just wanted to tell also, because y t minus p is that is the variable which actually tells you about the lagged past. So if I'm able to represent my values as a linear combination of my past lagged variables, that means the variable, that means if I'm saying a product sales, let it be a TV sales. Okay. So, in the current, if I'm selling a TV, this particular TV sale can be represented as a combination of the same model or same kind of TV, right, from the past, right? Right. So it can be represented by using the lagged variables. That becomes an auto-regressive model. Okay. So I don't know how much you understood that, but the current value should be a combination, a linear combination of the past. That's why I'm not even saying the word lagged. Forget about lagged. So if my current value is a linear combination of the past, then you can say it's an auto-regressive model. Okay, so why we are calling it as auto-regressive is because it is depending upon the regression model which we are going to speak. Now here you can see that y t minus p is basically the lagged values. Okay, and this phi 1, phi 2 you can see, which is the this particular this is called as a phi. Okay, so this phi is basically called as the coefficient of the model. Okay, and you can see the E part, which is at the last error term. Okay, so this error term is basically called as a noise, or I can say error. Okay, so we actually called in statistical terminology as white noise. Okay, so let me not go, again I have to discuss all those things. Just let us assume that it's an error. Okay, so I can just remember like that. It's an error term. That's why I just mentioned here as an error term. I didn't wanted to, just mention again as noise, again white noise and all those things. So basically it's a white noise, what we say, and it's basically called as an error term. And here your, where is this here only? Oh, okay, you can see the P here, right? So P is, here you can see what is the P is nothing but the order of the model. So this will give you this, it is basically y minus actually t minus k. So where your k values take from 1 to p. That means what you have to understand is that p indicates the number of lags in the data. So whether you are going, whether you are able to represent your current value, right, by how many lags you are going into the past data, how many lags you are going back. For example, you are going 3 lags, 4 lags, 5 lags. So at a certain point, you have to stop, because that with the representation with the coefficients for the past for the past sales, at somewhere down the point it will be equal to some lag, either it is 4 lag, 5 lag, 6 lag or 10 lag. There you will stop, right, building the number of lags. That is what your P actually represents, which tells you the number of lags in the auto-regressive model or the function which you are representing to, as a linear combination of your current value. Okay, so this is I try to simplify as much as possible. I hope, I think you have got, you maybe you would have understood. Okay, fine. And this phi, what we're talking about is the coefficient. Actually, we call it as a regression coefficient. Okay, we call it as a regression coefficient. This actually tells you the effect of the input variable and all those things. Okay, so that is why we say it's a representation of the, basically it's a representation of the linear combination of your past. Okay. Let me go into the project, right? And one more important concept is when we talk about the autoregressive model, there are particularly 4 important key assumptions. Okay, so 4 important key assumptions you will be encountering, or which has to be considered before applying this autoregressive model. The first thing is the linearity, right? So that is why we are applying the lag to the previous data and making it stationary, so that the linearity lies in the data. And the data has to be stationary. So already by this time, you already know what is stationary. Mean variance and autocorrelation has to be constant over a period of time. Then there should be no multicollinearity. That means the lagged variables, uh, the lagged variables should not have correlation among themselves. So multicollinearity should not be there, and white noise should not be there. The other term also should be independent, and we say it as IID in statistical terminology, independent and identically distributed. Okay, so you have studied statistics, when I say IID, they would have remembered this. So IID is a term which we use in statistics. So independent and identically distributed terms. So even the error term should be IID, which is independent and identically distributed. So that is in where we call it as a white noise residual. So white noise residual, multicollinearity, no multicollinearity should be there. It should be stationary and it should be linear. These are the aspects which has to be considered when we are building up, or you can say which are assumed before constructing a auto-regressive model. Okay. Now the properties particularly are the using the autocorrelation, then partial correlation, right? So what happens? What is this partial correlation basically is? In a very simple term, I'll tell you. I'll not touch much of this. You can just research it later because we have to finish the project as well, right? So I'll tell you what is this PACF. So PACF is nothing but partial autocorrelation function. That's why we call it as PACF. P indicates partial autocorrelation AC and then the function. So what does this this function actually PACF does is it will cut down where the model automatically will build. You need not sit and count how many lakhs we have to give. 5 lakhs, 6 lakhs, 7 lakhs, 8 lakhs. No, you need not sit and count. That is why we are using, Python programming, right? So you need not sit and count. What it does is, if you apply the PACF, it will cut down where it is actually reaching that particular amount of lakhs where the linear combination can be built, right? So when it identifies that, by using some 7 lakhs, the linear combination has been satisfied with the current value, it will stop going with the additional lakhs. It will stop there, 7 lakhs or 8 lakhs. Isn't it interesting? Yes, it is very useful. That is why without using PACF function, if we use autocorrelation, we are gone. Actually, we cannot use first of all. Okay, it will cut down the lakhs where it is forming that linear combination part. Okay, so this is what the autocorrelation is about. Sorry, this is about the PACF, and autocorrelation. Already you would have understood what is this autocorrelation. And next thing is the main assumption is basically using the forecasting models, which we are doing by using the autocorrelation. Now, so next is the I think you would have seen one particular line. Yeah, I just the one important thing which you have seen here is the lowest archaic information center, which is AIC. Okay, so what is this information criteria or information center is basically about? It's a metric. You can remember that. So for regression, you have seen mean square error. For for classification, cross entropy, like that. It is a metric. Okay, so what is this metric actually does? In a simple term, you can remember that this AIC, there is one more name for this AIC, which I have not mentioned here. Okay, so the one more name for this AIC is the Bayesian information criterion also. You can say archaic information center, which is AIC. I would rather say remembering Bayesian information center, BIC, is more easier. because everybody knows Bayes and Thomas Bayes, right, for conditional probability, right, and Bayes theorem, right, Bayesian inference and all. So Bayesian information center or information criterion, you can remember. So when I say this is a metric, you would have already understood that what it does. It's a metric to choose the optimum p-value where my model PACF has to cut down the lags, where it has to stop that particular place, or that particular, it will try to evaluate that, yes, this is the correct p-value where the model has actually cut it off. Okay, so this is what we are going to do. Now let us go to the model building. Okay, so we are defining the values here from 1 to 4. Okay, we are defining the p-values for 1 to 4 for time being. Now let us go to the moving average model. Okay, so before building ARMA, see, because basically there are 3 big models. Okay, AR is autoregressive model, MA is a moving average model. So there are independent models which are there, but the biggest models which are used are the main models, I can say, or the big 3, Fab 3, right? So which is used for predictions are the ARMA, ARIMA, and SARIMA. So to understand ARMA model, ARMA is basically a combination of autoregressive and moving average only. So independent, individually, AR is one model, MA is one model. So combining them, we are using as a one model, which is because AR cannot be used separately, MA cannot be used separately for predictions. Yes. So these are just models which are used to calculate. So combining this as an ARMA model or ARIMA, which is ARIMA, and applying the seasonality, which is the SARIMA. For these models, you can use the predictions, because time series is used for predictions. No, if there is no use, you cannot predict the value, then what is the use of building the models? Not required. No, that is why AR and MA individually, they are not used for predictions, but combining them can be used for predictions. This is what also you can keep it in mind. Now, coming to the next part, which is the moving average. Okay, so moving average is basically, I can, for AR model, again, I just thought of telling one key point also. For AR model, so to build an AR model, usually we try to, use the stationary checks, choosing the order of how the P fitting the model and all already we'll try to do that, right? So that is what we are trying to do. But AR model individually is not very that good, right? So we can use it for predictions, but in a shorter note, if I say, to be fair, openly, not that great, okay, individually. That is why we are mixing with the MA model, which is the moving average. Then the, when we mix your autoregressive model with your moving average, it becomes like a beast, okay, and including the trend part, and also including the seasonality part, even more, it becomes a bigger beast, right? So for predictions and building the model, okay. So this is how you can understand or picturize in your brain, because if you already know this, it's good. If you have already the first time, if you are hearing, it may look like little different, because these are very standard models which are existing, I can say, from past maybe 70-80 years, I can say. These moving average models have been built by statisticians and mathematicians. So now little modifications and all we are using in current day machine learning and AI stuff. Okay, so now let us understand what is this moving average about. So moving average is basically trying to predict the current value, right, as a linear combination, right, of the past error terms. Okay, now this may seems little confusing. Okay, fine, I'll try to simplify it. Now in the autoregressive model, right, in the autoregressive model, what I told, build in the current value as a linear combination on the past lagged values. Correct now? Now what I'm saying, now what is moving average? I'm telling moving average is a linear combination, right? The current value is a linear combination of the past terms. So now instead of that lag, now I'm using one more new word, right? One more new word, which is, trying to predict by using the errors or the white noise in the data. Okay, so this seems a little different from, what we have understood by the auto-regressive model, right? So this is a little different. Now, in this model, if you see that mu, if you take mu or epsilon, anything is okay. So in this model, you can see that there is a error term. So it is basically more focused on the errors. Okay, and here you can see that Q is nothing but the lag in the data. Okay, or you can say order of the lags in the model. Okay, now to understand what is happening particularly inside the in the MA model, the main focus is on the past terms or the past errors. Okay, and we are particularly using on the error terms, and we are using on the which is the IID, which is identically independent data, and then which is used on the short-term memory. Okay, I'll come to the short-term memory when we are discussing NLP also, where there is something called as a long short-term memory. So this short-term memory is nothing but diminishing after, or you can say forgetting. Okay, memory where forgetting after a few lags. Okay, and then it also focuses on stationary as well, right? Now, when we talk about the the main functions here, there are two things when it comes to the uh, moving average model. Two important things are the ACF. Okay, so autocorrelation function, and also we talk about the PC. Here I've not mentioned, it is PACF also, partial autocorrelation function also we talk. So now, to understand what is autocorrelation happening here is, it actually cuts down the lags after the optimum lag has been met. Okay, and the first Q lags, or that means the amount of Q where the maybe first 10 lakhs, let us say some 10 lakhs is the optimum number. We have to if we have to build a moving average model, this first 10, which is the optimum value of Q, this first 10 should have a significant autocorrelations. Okay, so this is one thing we have to keep in mind. And one more important thing is PACF, which is the partial autocorrelation function. This also has to be decreased, or I can say decreased particularly, I can say exponentially, right? So this has to decrease exponentially if the lag actually increases. Okay, so this is what you have to keep in mind. Fine. So now let us move a little forward. Okay. Applications, I would think, in a simple way to make you to understand, I can say, for stock prices, we can use the moving average model. It will be a good fit. And we can use for weather predictions. And we can use it for sales data as well, because we have random shocks, right? To identifying the underlying patterns and all, we can identify for the sales data. So to actually, to summarize on a very small, small aspect of what is AR and MA model, because once I explain AR and MA separately, you're able to figure it out ARMA, ARM, ARIMA, and SARIMA very easily. So that is my, focus is also. That is why, I'm trying to break down more of auto-regressive and moving average. I'm trying to even more simplify to make you to understand. Okay. So if you have any questions, you can just ask me. I just want to tell something. So behavior and all I just finished. So maybe, yeah, I'll just go to the auto-regressive model. Let me finish this, then I'll just take your questions. So here you can see that for this model, we have to define the Q value, right? And we have defined the Q from the range of 1 to 4. Okay. And now we are iterating the values. We are applying the 3 parameters, which is P, D, and Q, right? And we are iterating over the models. Okay. So we are iterating for that P, D, Q. what are right. So D is basically the differencing, and where is this? P is for the AR model and Q is for the MA model. Okay, and we try to calculate the range, and here we are giving the differencing with 2. Okay, and we are applying for both the ARIMA model and ARMA model. Okay, so we get the values here. Let me scroll down. And yeah, let me just go up again. Okay, fine. So just ask me. It's actually again a flow. I have to explain it in a flow. Maybe you can just explain. You can just ask me till here if you have any doubts. Yeah. So, ma'am, I shared the attendance link also. I can just fill in the attendance link in the feedback form. So in the meanwhile, you can do that, and you can ask me the questions also if you have any. Fine. So if you don't have any questions, I'll move forward. We have a lot to discuss anyway. Okay. Fine. Okay. So here we have discussed we have given the range, okay, of the Q value. Now, as we already have seen what is P and what is D and what is Q, okay. When it comes to the uh, you know the model which we have done in the AR model and what we have done, what we can give in the moving average model. So now, basically now what we are trying to do is we are also trying to combine both the models, right? By giving the uh, you know ARMA model. Okay. So now in the ARMA model, it is first of all more focused, right, on both the things, which is the AR and MA. Okay, so here we're trying to build using the AR model, and then we are using the ARMA model. Okay, and we are trying to predict the values. Okay, so here we are defining the differencing for 0 for the AR model, and for ARIMA model we are giving the triplet. Okay, and for SARIMA model, which is we are defining the seasonality as well. Okay, so we are trying to define the variables first, and now we are trying to build. So for all the three, we are predicting this AR model, right? And then ARMA, and then PDQ, as well as the seasonal. Okay, for all the four, we are trying to build an array. Now, the next thing what we are trying to do is we are applying, the separation of data, right? Here we are applying the data into two parts, right? So the data which is less than 1st January 2013 for the training data, and for the testing data we are putting the data which is greater than or equal to 1st January 2013. So basically, based on dates, we are trying to divide the data into two parts. Okay, and then we are trying to apply the Dickey-Fuller test. Okay, now after that, since you're already aware, we are also going to apply the log transformations on the data set. Okay. Now, coming to the values of what we got by using the AR models, right? So we have built a model using particularly the value of P first, right? So now you can see this is a very important table. Okay, let me go to the table directly. Okay, so this is a very important table what we have actually built, okay, for the ARIMA model. Okay, now the most important thing what you can observe in this table is the value of the sigmas. Okay, so for example, you can see the coefficient values, standard errors, and then the z values, then the probability of which is greater than or equal to z value, then your confidence intervals, which is from 0.0252 to 0.975, right? So basically, we are using the 95% of data, we are giving the confidence interval values. Now, since we have segregated the data, which is into two parts, right? We have applied the lag part also, and we have calculated the value for the number of observations, whatever we have. So I think totally we have around 120 observations in the data set. Now, so after the model has been built, right? So we have outputted the model, or we have got the output. The next thing what we are trying to do is we are trying to calculate the root mean square for the AR model. Now we are for the auto-regressive model, we are trying to forecast the values. Okay, we are trying to forecast the values, and we are trying to predict the error, what can be the possible error for the forecast, right? So because we already know, because true and predicted value is what the difference between that root mean square error or mean square error. So here when we see that the forecast values are around some 306, which is the error what we have. Actually, it is a great error. Okay, it's a huge error. Now, once the model has been built, right, we try to plot both the both the values, true values, as well as the predicted values, or you can say, sorry, forecasted values. We should use the word forecasted here. So here you can see that if I put the forecasted values, okay, and if you see here, this blue line indicates the trained values, and orange indicates the testing values, and see the forecast. So it is not that great, you can see, correct now? Now, that is why, see, the forecast is not that great. The predictions are not that good. See carefully, correct now? Where is our forecast? Where is our sales, the testing values? So it should be near to the testing value, right? So it is not in a very good, prediction, or very good, what we have actually built a model. It's not that great, right? So now what we are trying, because with this error, this is a huge error, man. It's a very huge error, which we have been able to identify by the ARIMA model. Now, if you see carefully, yeah, this is just about ARIMA and ARMA model. So let us directly apply the ARMA model, because already you have understood that what is that ARMA model, ARMA. So it is basically a combination of both the autoregressive and the moving average. So autoregressive gives you about the series of past values. Moving average tells you about the error terms in the past values. So already you would have understood by this. So let us not go again into the mathematical things and all. So you can just apply the ARMA model now to the data frame or the data, right? And you can see the AIC values, right? So we have already talked about this AIC, right? So what is this AIC basically is? So, right? So it's basically that, Bayesian value, okay? So you can remember as Bayesian value. And in this AIC, I think I just wait. I'll tell you. A cake, yeah, a cake information, a cake information center or information criterion, right? A cake information criterion or Bayesian information criterion. So you can you can remember like that AIC value, okay, or BIC you can say. So we usually call it as AIC here. And here you have built, a parameter for the AIC value. And when we have calculated, okay, so when we have calculated the AIC values, you have got many AIC values here. You can see for different values of P, D, and Q, right? Because those are the three values which we have defined. Correct, no? P, D, and Q. So here we have taken D as all 0, differencing as 0. So P value is 1 and Q value is 1. This is the AIC value. P value is 1 and Q value is 2. D value is 0. So P, D, and Q, that is the order we have actually defined. And that's the order of what actually we use. So we can see the AIC values have been built. Now, if you see by the values, by the most negative, you can plot a graph to sort by the ascending order, because it's a negative value. So the smaller value comes at the top, because minus 346 is greater than the minus 383 because it's a negative value. Now, so next for ARIMA model, we are trying to summarize the data. And for this ARIMA model, you can see again the coefficients and the sigma values. Okay. Now, next what we are trying to do is we are going to build the MA model. Okay. So for this MA model, we are trying to forecast the values of the sales. Okay. And here we are trying to calculate the mean square error. Okay. So for the mean square error, we have around 225, right? RMSE we are taking, again, that is also high, right? So root mean square error should be very less. So we have already discussed on this. Mean square error and root mean square error should be very less as possible, because they try to, they calculate the actual versus your predicted values difference. So, logically, if you think it should be very less, then only we'll be able to predict the values for the, then only we can see that, our prediction and the true value is actually same or almost same. So it is very important for us to make them or to identify that, they doesn't have much difference. So it has to be, close to 0 as much as possible, right? And now going down to plot the sales, you can see that the forecasted values are somewhat different with the, somewhat better with the tested values, but still they are not that great, right? So this is again, we are plotting the values for the moving average. Okay. Now, here we are trying to, this is what we have actually done. So we have applied both the combinations. Okay. That is ARMA model, and we are applying the differencing, right? Which, helps, or you can say which identifies the trend in the data. So including these two, you can call it as an ARIMA model. Okay. So ARIMA is basically auto-regressive integrated moving average. So that integrated means nothing but the differencing. Okay. So yeah, here you can see. So integrated is nothing but the differencing component or the transformed component. Okay. Now I'm building the ARIMA model, and now here you can see that your D values are 0 or 1 or 2, or I think all 1, maybe 0 and 1 maximum. So here we have started with differencing because ARIMA model itself is dependent upon P, D, and Q. For ARMA model, ARMA, we don't take the D value, which is 0, because we don't apply the differencing techniques. So for that, we don't see, we have not seen much of a good prediction. So because why we are not able to see is it is bringing in the trend and the seasonality also. That is the reason we are not able to achieve good results from the ARMA model. So now you can see the building on ARIMA model, and you can see the results. Okay, now I'll show you the graph. Okay, so now the graph has somewhat improved from the from the ARMA model, if you see carefully, right? Now if we go down, okay, this coding part I'm leaving it to you. You can understand it very easily. And there's, it's a standard syntax is what I've used. Only the variable names and all I have just changed. Okay, so you can just try and understand. Okay, so next, coming to the next part, which is the SARIMA model. Okay, this is one complicated model it is. So because this model actually brings in not only the trend but also the seasonality into the picture. So keeping this in mind, here we are trying to introduce the seasonality factors as well as the trend and the seasonal factors. Okay, now which is we are denoting with the capital P, D, and Q. So don't get confused. P, D, and Q are non-seasonal factors, and P, D, and Q, which are the capital, are the seasonal factors in the SARIMA model. That is what I told. This is a little confusing part. Okay, because the variable name itself is confusing because capital P, D, and Q are the seasonal factors, and small p, D, and Q are the non-seasonal factors. So now we are bringing in the autocorrelation part, and we are trying to build the SARIMA model. Okay. So now when we build the SARIMA model using the SARIMA model function, right? We can see that there is a lot of seasonal changes which are actually there. Now this inference is very important when this is what I just wanted to explain, which is a very important value. Which is very important. So here you can see that the seasonal values, right? So which is you can see the first part here, which is 313, right? So that is the first part of P, D, and Q. That is non-seasonal changes. And the next part, which is 313 and 12, is nothing but the which is the seasonal changes. Apart from that, they have also the S factor, which is the time span, which is the 12 months, which we have taken. Now we are building the SARIMA model, right? Now we can see the truck sales with the actual and the forecasted. Now after plotting this, you can see the difference in the forecasted and the testing values. They are almost similar, see. Right? So now you understood how that trend and seasonality, if it is existing in the data, then definitely you have to use the SARIMA model. So if I directly tell ARIMA skipping it and then go to SARIMA, you'll not be able to figure it out. But when you have seen each graph, now you would have understood that, okay, so if the data is having a trend and seasonality in the data, right? So it is very important that we have to use the SARIMA model, right, with the parameters P, D, and Q, which is non-seasonal, and again capital P, D, and Q, along with the S if it is having all the 12 months. So that is how we are going to forecast the model, and we are going to build the 95% confidence intervals and also 99% confidence intervals, and we are going to predict the forecast values along with the upper confidence and the lower confidence interval. That means here you can see 95% confidence interval. We can predict here we are predicting the value between 447 to 518, and our value, the forecast value is 481. Okay, and it is between, so confident, how much of confidence interval or how much of confidently we can tell that our forecast value lies in that particular interval, right? Or the real value lies in that particular interval is what the confidence intervals is basically about. And then you can see that the observed and the forecast values, okay, they are very similar, and based on that you can take the forecast values, whatever forecast values here you can see. the forecasted values, what we are considering for the future forecast. Our data is only till 2013, right? 2013 or 2014? 2014. From 2015, we are forecasting the data. That's how the data can change. Okay. So this is what actually we have identified. Okay, 4 important things from the plots what we have done. Okay, and which are useful for identifying. So I can just go through the project line by line. Okay, you might be understanding as well. So just give me a minute. I'll share it as well. Just give me a minute.
So we'll wind up for the research. If you are done.
Yes, ma'am. Just give me a minute. We can.
Yeah, sure. No problem.
Yeah. So I just shared in the chat. You can download it. I'll share it with ma'am also. She'll upload in the LMS. So yes, ma'am. We can wind up.
Yeah, okay. So thank you so much for your valuable class. We'll again meet on Monday. As students, you all know Saturday and Sunday we don't have a session. We are meeting again on Monday. Okay. Thank you, sir. Thank you for your class. So,
Sure.
thank you all. Thank you for joining this session. We are winding up for the day. Thank you. Good night.